This first slide consists of differentiation rules or rules that you can use to take derivatives of functions. The first rule is called the constant rule. If you take the derivative of any constant, like a 3, a pi, a -12, an e, any derivative of constant is 0. If you think about constant graphs, they're horizontal lines which have 0 rates of change or 0 slope. The power rule is very powerful to help us take the derivatives of algebraic terms. For example, the way you read this notation is if you have a function or a term, excuse me, let me just do a term. You can do it a function also, but you multiply the coefficient times the exponent, and then you subtract 1 from the exponent. For example, if we had something like 2x cubed, then its derivative would be 2 times 3x, take 1 off your power. It's very simple, and these derivative rules allow us to stop having to use the limit definition when we're taking basic derivatives. The constant multiple rule, that's just if you have a lead coefficient, you can multiply it through your function and take the derivative, or you can take the derivative of your function and then multiply it by the constant. It's kind of dealer's choice. Sum and difference rules, if you have a couple of functions either added or subtracted, you can take their derivatives separately, add and subtract. So let's look at several examples. Let's take the derivative of each function using derivative rules. You guys did really well with this in class, by the way. Let's start with a constant function, y equals 3. Remember that any constant function will have a derivative of 0. Our next function, g of x, 1 times 5, that's 5. Subtract 1 from your exponent, and that makes it 4. The third example, 1 over x to the 4th, remember that your exponent properties will allow you to bring this to the numerator, but you have to change the sign of your exponent, and that's fine. You can always do that. 1 times -4 is -4. Subtracting 1 gives you -5. Returning your x to the denominator will make your 5 positive. To the top right of your screen, I wrote the property where if you cross a fraction bar, you change the sign of your exponent. There's another exponent property, and it's tied to radicals. If you have a rational exponent, the number in the denominator is your root, and the numerator is the power. We're going to use that for this first function at the top, y equals cube root of x. You can rewrite that as x to the 1/3. So when you take the derivative, you have 1 times 1/3. 1/3 minus 1, -2/3. Returning that x to the denominator and translating 2/3 back into cube root of x squared, you no longer have negative exponents. In the second example, we have a function with 3 terms, -4 times 2, that's -8. Take 1 off your power, that leaves it with 1. Move to your second term, 7 times a power of 1, that's 7. When you take 1 away from this power, you don't have any more x's left, so it's a constant. And then your third term is a constant, and its derivative will be 0. You don't have to write plus 0. Our last example, we have 3x to the 4th minus x squared plus x plus 5. Taking the derivative, 3 times 4, that's 12. Take 1 off your power, that's 3. -1 times 2, that's -2. Take 1 off your power, that leaves it at 1. 1 times 1 is 1. Take 1 away from your power, no more x. 5's constant, so it has a derivative of 0. The derivatives of sine and cosine, and the derivative of the natural exponent function e to the x. Derivative of sine equals cosine. Derivative of cosine equals negative sine. You'll have to watch that sign change. In class, I drew the graph of sine and briefly described how you can get the derivative graph, which turned out to be cosine, using our properties of max and mins and rates of change, whether the graph was increasing or decreasing. E to the x is special. It's the only function that has its own derivative, and later in the class, it'll have its own integral. Pause if you need to write those down. You can find these in your Google Drive folder as well. Take the derivative of each function using derivative rules. This first function, we have an algebraic term 3x squared. We know how to take the derivative of that. That's 6x minus 5. The derivative of cosine x is negative sine x. Those two negatives will make a positive. In the second example, negative 3x is also algebraic. Its derivative will be negative 3. 2 times sine x, that'll be 2 times the derivative of sine x to cosine x. Third function, we have g of x equals 4e to the x. So this is an exponential function. And we also have a trigonometric. 4e to the x, as long as it's e to a single variable, its derivative, you just recopy the term. Plus 4 times the derivative of cosine, which is negative sine. That's why we have a sign change in the middle.